So today for short presentation, I would say, I wanted to talk about some concepts that are quite old, but largely used still nowadays, that are called S.O.L.I.D principles. So in this presentation, we'll see why those principles were invented or created, so to say, for which situations, and then see which are those five different concepts and how they can help to improve the code quality in general. So those principles were initially written by Robert C. Martin, a very famous developer in US in the year 2000. And a bit later, the acronym itself, S.O.L.I.D, was invented and the concept developed by Michael Feathers, another coder. Sorry. So why those principles were needed at some point is because in the code and the software development, the applications are getting more and more complex nowadays, or for a long time now, with more and more interactions between applications, more features, more complex operations. And all this leads to bigger piece of code that can become very hard to read, big blocks, long classes, and so on, which obviously reduces the efficiency of people reading the code or trying to work with it, even if the code works well by itself. Also, on the other hand, the modern standards of coding requires a lot of flexibility, reactivity, adaptation to new specifications, to new concepts, to new problems found more and more. So this also brings the need to have simpler code, so to say, but still more and more powerful. Of course, the maintenance of the applications is a big topic, because application working today is good. If they can keep working well in the future, it's even better. And if it's easy to maintain them, to keep them working, it's nicer, of course. And last point is the reusability of the code itself, either by extending it or sharing it with other developers, other applications, can be complicated if the base code itself is not properly designed, so to say. So applying those principles comes with great benefits, of course, and some cost. The main one being increasing the designing and writing time of the piece of software, because there are usually more classes, even smaller, but more classes, more interactions, more thought about which class does what and which piece of code is needed, which one is not, much more reflection ahead, so to say, before even writing a single line of code. But at the end, it brings us with much more, much stronger code, easier to maintain, much faster to find bugs when they are, and there will be always. It's like this. But the code is easier to read. Some situation can be understood even without running a test itself. And it's also easier for someone else to use the code to extend it later or even share it with a community. Everything is kind of easier when the code base is clean. That's it. So starting with the principles, the first one that stands for the S of S.O.L.I.D is the single responsibility principle. This one is one of the widest well-known principle that's applied in many solutions already, even without noticing it. So the basic of this principle is one class does one thing. That's simple. So no big class doing all the work for the whole application, but instead of that, having smaller classes doing their own stuff, and not having reasons to change if they are not concerned in the new requirements. This brings easier testing phase because there are obviously less test cases per class. So it's easier to test one class and get rid of the test phase faster with this class. Lower coupling, of course, because less functionality in a class usually implies less dependencies as well. The coupling is actually the interaction, the links between different classes, different objects, and the more they are, the harder it is to maintain the code and to make it evolve without breaking things on the way. The organization itself is also easier to understand and to read with small class, with few methods, less lines of codes than big class that do everything in the app. Is hundreds or thousands of lines of codes to read when we need to find something in this class behavior. And it's at the end also reduces the anticipated side effects when we change something in the class, because the point of the code is, as we usually say, to not reinvent the wheel each time. So the code has to be reused in future applications. And the less impact, bad impact we can have by changing a line in a class for all the others that are depending on it or extending it, the better it is, of course. The second principle, the O, is open-close, which actually is a short way to say open for extension and close for modification, which is connected to the first principle. That means a class should be, we should be able to extend the class to extend its functionalities, what it can do, but not touching the core of the class. The code itself, when we build it, it evolves. We have to change some things, to add new features and so on, until a certain point where the code, the class, does what it was meant to do. And from this point, this core should be closed, fixed, and kind of frozen for modification later, because this is what the class is supposed to do. And anything else would have to be an extension of this class, a new version, so to say, a new concept added to this class, not modifying the core. This brings, of course, better structure because we can rely much more on the core of the class that will not change, and having a lot of flexible layers on top of it to extend the functionality, but still be sure of what is inside, what is under this. It also reduces the risk of bad interaction when we change the class, or when we extend the class. There are less risks of breaking something else that is using the base class itself, the base of the code that is in this class. The only cases where it doesn't really apply is for bug fixing, of course, because the bugs have to be fixed in the base of the class, because that's something that doesn't work well, and it has to. It's not a new feature. And that's where we have to change the class base itself and not the extensions. Apart from that, everything else should be actually extending a solid core and not changing it later. The third one is the Liskovsches substitution. This one is the trickiest to get and to explain, actually. It's tightly linked to the inheritance of classes. And it states that if an object is children of another object, then we should be able to replace the parent by the child without breaking everything in the class behavior itself. The main benefit from it is consistency in the code, and avoiding bad design that could be hidden in the code and breaking the code later without knowing exactly where it comes from. It's also easier to extend a software that is following this principle, so to say. This principle itself can be a source of longer design phase, of course, because this brings more questions about, as I said in the introduction, what the class is doing, what is its responsibility, what are the limits, and so on. But globally, there are there are many topics talking about it, and there are several hints to avoid breaking this principle. One simple checklist, for example, would be when extending a class, the overwritten method should not introduce new exception types, for example. If there is an exception, it should be the one that was planned initially, or an extension of this exception. So we are sure to not bring new problems when using the child instead of the parent in a piece of code that was expecting the parent's behavior. The preconditions should not be stronger than what they were initially in the parent class. If your parent class was, the method in the parent class was expecting an integer, it should not be in the child expecting only positive integer, for example, because this would break any other piece of software that works with the base class with negative, for example, negative numbers. In the same way, the post condition should not be weaker than initially, so we should not allow weaker conditions when exiting the overwritten method than what it was in the parent one. Otherwise, that could lead to unexpected behavior later after execution of this method. And the invariant should not be changed, of course. If they were meant to be invariant, they should stay invariant after executing the overwritten method. So yeah, that's globally about inheritance and what children should do compared to the parents, and so on. And next and fourth point is the I from S.O.L.I.D, the interface segregation. So globally, it's about using separate interfaces to describe the behavior of classes instead of one big interface, one big list of methods that do everything in the class. That is actually a way to avoid useless code in some cases, in some situations, and also that can help to decouple the code and not having interaction that were not supposed to be. There is one simple example for this that goes around a zookeeper, for example. If we say that the zookeeper are taking care of the bears, for example, they can do several things as zookeepers. Or a zookeeper taking care of animal can wash the animal, can feed the animal, can pet the animal, for example. So any member of the zoo that is a zookeeper, so understand, implements the interface zookeeper, and doing those three actions, has to do those actions. Problem is, if a zookeeper is taking care of a dangerous animal, the pet animal action can be a bit complicated for them, and they might want to not do it. But if they are zookeeper, they have to do something when we talk about petting animals. Instead of that, there could be three different roles, three different interfaces instead of zookeeper. There could be a pet cleaner, a pet feeder or breeder, and a pet petter, an animal petter, so to say. And in this case, the members of the zoo could be any of those three roles, or three at the same time, but those who are taking care of dangerous animal, they could avoid doing the pet interaction and leave it to some other more crazy people. So that was an example to say that if a client doesn't need a feature, this client should not be forced to implement it or to find anything to fill in this feature for no reason. So that's the purpose of interface segregation. And the last principle that's quite important actually is the dependency inversion, which means that we should rely more on abstractions than on concretions. And that is actually most of the time already implemented in professional solutions. So we don't even always see it, or we don't notice it, but it's there. It can be achieved by different ways. One of the most common is the dependency injection, which means actually bringing the dependencies in the constructor of the class to be used there instead of instantiating them inside the class. So actually the coupling is broken there, and it makes the class much easier to test first and to reuse in different other cases. And yeah, the one typical usage of this is the adapter for the adapter design pattern, actually, that is used for data manipulation, for example, in applications that are using data in database in whichever format, files, SQL, and so on. The adapter, for example, is usually an interface implementing the method to fetch data without caring of. So we can call this method to fetch data without caring about how it is done actually. Just the adapter implementation will do it the way it's the best, with SQL queries for database, with file reading for files, and so on. And the higher level module doesn't really care about how it's done. So all of that to say, those principles are old, still used, and unfortunately they are not the only solution to have robust and solid code, but they are good practice, and they should be used anytime we are designing new piece of software. They are better used with other methods like agile, case, design patterns, as we already talked about a bit. That brings the whole of them actually bring a good synergy between the different parts of the software, the different development phases, and so on. And it could be seen as a good first refactoring step when we need to go deeper into a code to refactor it, to make it cleaner, to make it simpler. Following those principles, applying those principles, checking if they are actually respected, and applying them if not, could be a good automatic first refactoring step before going deeper into changing the logic of the code itself. So that was it. Thank you for watching and listening.
Thanks a lot, Vincent. I really like the zookeeper example. I think it's always good to have examples that are really easy to understand, so things come better to our mind.